Okay, great. Great. So we're going to get started right away with our special guest today because Dr. Hugh Hudson, who is sitting over in Glasgow, and it's 1 a.m. in the morning. So we are going to have him just take it away. But I first want to I want to tell a tiny little short story, which is that when I worked at the University of California at Berkeley at the Space Sciences Lab, I was sitting in my office in 2012. Maybe it was 2011 actually. And Hugh walked in because Hugh also worked there as a solar physicist and said, there's going to be this big eclipse in 2017 that the path of the totality will go across the entire US. And we want to see if people will take photographs of the corona during totality. Do you think you and your team could make that happen with us? And I was like, yeah, yeah, I think we could. And he goes, well, I'm not signing you up yet. I have to talk to a bunch of different people and see who should really be doing this work. And I was like, great, well, come back if you're if you think but we're in if you want us to be in. And then sure enough, so he was the reason that we did this project. And amongst two others, I think but you can tell the story, Hugh, that you had at that conference that you had just come back from. So I thought we could start there since you started it all. And then you
Well,
can
that's
go.
right. Was it back in, was it 2012, as early as that?
It was at least 2012. It might have been 2011 because we got together at HAO in 2012. That was our
Okay,
first
well,
meeting.
yeah, so I can say that I was actually in the room where it happened, right? I don't know if you've seen Hamilton. You have seen Hamilton. If you haven't seen Hamilton, see Hamilton. That starts, that has that great, lots of great things, but one of them is about I was in the room where it happened, you know. So yeah, I had come back from Boulder because the idea had appeared in a conference there, and so this was going to be a new good thing, the Megamovie, and so as it turned out, thanks to Laura, it became a good thing, and the idea still lives on as you all are a part of it, and I kind of because I've moved to Glasgow and I'm very retired by now. I won't tell you how old I am, but it's really old. So I sort of detached myself from Megamovie, but I continued with the smaller part of Megamovie, which I'll talk about. And so the smaller part we called Sun Sketcher. So can I project stuff, or
Yeah, you should be able to.
I will share a screen? And what I want to do sort of is just give you basically an overview science kind of presentation and some anecdotes about the eclipse in 2024 and the partial in 2023, which is a part of the SunSketcher business. But so I'll start first with some background astronomy. And so all of you are interested in astronomy or are astronomers, so you know I don't have to tell you a lot about how the sun works and eclipses and things of that sort. But I'll skip over a lot of this background stuff. What I'm doing is I'm showing you slides that I made for a eclipse meeting that we had here in Edinburgh,
But we
and
haven't seen him yet.
you haven't seen my slides.
Right.
Here they come. Here they come. I'm sharing. Okay, it's going to be. It's always I need to find the proper window. It is PowerPoint. Share. Um, are you in fact seeing it?
Yes.
And
We
is
can
it
see it's not in the slideshow version.
swap
Now it's
display?
in, yeah, swap displays. There you go. Perfect.
Is that good?
Yeah.
Okay.
Can you click on continue to share? Do you see that?
Yes. Yes.
Awesome.
But what does that do?
I don't know, but you're sharing. It's all good.
Okay. Okay. So this is Mega Movie and Sunsketcher, and the Sunsketcher part of it is I will describe it. It was hosted at the University of Western Kentucky uh, by an old friend, Gordon Emsley there, who was a solar physicist person, but who was entranced by this idea. And so the idea was to measure the shape of the sun And this is sort of basic solar astronomy. Uh, which slide are you seeing? You're seeing the basic solar astronomy slide?
Yep.
Okay. So yeah, basic solar astronomy is just things like how bright is the sun, that's the solar constant, and what is the shape of the sun, and global properties. So our idea, the sun sketcher idea, is in the category of making a very precise measurement of the shape of the sun. And the shape of the sun is related to the brightness of the sun. The brightness of the sun fluctuates. It was called the solar constant through the 19th century or something like that. But then it was this great uh, what was his name? Forgetting, but some American astronomer decided that no, didn't have to be constant. You could measure its variability. And he tried very hard. He thought he had succeeded, but he really hadn't. It really wasn't measured to be variable until 1981, 1980, 1981, when the solar maximum mission was launched. And so now this bottom graph here shows you the solar cycle. You can see that the brightness of the sun goes up and down, and the amplitude here is expressed in watts per square, I think watts per square meter, uh, with a baseline way down in the basement. This is just a tiny fluctuation, like a tenth of a percent over the solar cycle. And it can be modeled because most of the variability of the brightness of the sun comes from sunspots, which of course are dark, and faculae, which are of course bright. And it may be amusing to you to realize that the faculae are actually brighter than the sunspots are dark, so that at solar maximum, when you've got lots of active regions, the sun is actually brighter, in spite of the fact that it's loaded with sunspots. So
And
that's
the
an interesting.
and Hugh,
Yes,
the faculae are that kind of like the stuff around the sunspot, right?
right, right. So a sunspot is a gigantic magnetic field, right? And so the magnetic field is very concentrated in the dark sunspot, but it spreads out through the corona and comes back down to the photosphere into these patches called faculae, white white light, and they're quite interesting because they're not really very visible on the disk. You can see them very strongly at the limb uh, because the directivity of the radiation limb darkening law for the faculae is different from what it is for the quiet sun as a whole. So anyway, that's all solar constant stuff. Um, and then this is showing an early attempt to measure the radius of the sun as a time variable. And that has never successfully been done. But this graph shows you a very interesting sequence starting from 1966 through 2010. People make the measurement delta R, how big is what is the radius of the sun in arc seconds? And over here you can see that the numbers are half an arc second. This whole range is 1 arc second, let's say. So here are people's points, and here are these error bars on the points. And in this field, it's quite characteristic that when you make a measurement, you underestimate how bad it is. So the points are all over the place on this scale, but the error bars are tiny. So there are two ways to think about this. One way is that, well, maybe it's really highly variable and the error bars are correct. The other is that, no, your measurements are not so good and it isn't so variable. And the latter is the case, I'm quite sure. Okay, so this is a formidable task because here you've got this gigantic sun, which is really pretty solidly rock solid, uh, stable, except for this little variation you see in the brightness, and the radius can't be measured. Okay, so where does Sun Sketcher come in? So I'm just going to go down and show you what possibly could make the sun not be round. So that's one, uh, which is what we can measure with Sun Sketcher, as I will get to. So the various things that can make it not be round are rotation because of centrifugal force, pulsation because the sun is vibrating in lots of modes, convection, you can see that in the surface in terms of photospheric granulation and supergranulation, and not to mention spots and things like that. And this generally magnetic field, which is by its very nature, the magnetic field is not spherically symmetric in its geometry.
Hugh, there's a question about what specific wavelength is this I assume this is the photosphere, but is there a band that people are typically, is it just the visible?
Well, that's a really good question. So yeah, you can measure the size of the sun at any wavelength you want to. The sun is very bright at optical wavelengths, and also in the infrared, and also in the ultraviolet, and also in the at radio wavelengths, and also in soft X-rays and hard X-rays. So it's just an amazing object, and at some extreme wavelengths, like if you go to hard X-rays or let's say 100 kilovolts photons, really powerful photons at 100 kilovolts, the sun is actually dark. And so you would, if you could observe make images at 100 kilovolts of sufficient uh, precision, you would see a black shadow against the starry sky behind it. So that's the so at longer wavelengths, it's just bright, and at the very longest wavelengths, of course, as Laura knows well, the radius of the sun extends to where the Earth is. Right, this is kind of uh, the solar wind, and so we're actually swimming around on the Earth through this outer parts of the solar atmosphere, which are always expanding. Okay, so anyway, that's different shapes of a star, and that's a star, a pretty roughly two scale description of a star whose name I cannot pronounce, but maybe one of you can. I would probably try to say Achernar, but it's the champion rapidly rotating star Alpha Eridani, and it's going so fast that it really is oblate just in this shape. And because it's oblate, it also has a very non-uniform surface brightness. And that's a technical thing called von Zeipel's theorem. Okay, and of course those are the p modes. You don't care about that. I want to get to the point here. This is flares, uh, totally irrelevant. Okay, so Sun Sketcher. So what is Sun Sketcher? We tried to do this with the original Megamovie in 2017. Laura, you will remember. The further idea
I do.
after uh, the great thought that cameras could make movies of the corona just in the hands of talented amateurs, as you're doing. You can also actually use smartphones. And so the smartphones don't let you make very good images. I mean, their cameras are wonderful, but they do have the amazing ability to contact GPS. And so with GPS, you have the ability to measure time very precisely. And with the smartphone camera, you can measure the Bailey's beads. You can time them very precisely. So those facts coupled with the uh, knowledge we have about the moon, the surface structure of the moon now, we can use that as an astrometric reference during an eclipse, look at Bailey's beads at the exact times Bailey's beads appear and disappear, and then thereby get a measure of the radius. So this is not a new idea. People have been doing this, ever since. But with the smartphones, you've got the ability to make the measurement in the hands of everybody, right? I don't know what fraction of the world's population has a smartphone, but it's got to be a substantial fraction. And of that, a substantial fraction, almost all of them have got GPS. And so let's enlist all of those people and get them to not do selfies, but look at the sun through their smartphones. And here there's a story. All right, Laura, you probably are familiar with dealing with NASA about this. NASA obviously is a very good agency to work with on a program of this sort because it's an outreach program, and at the same time, it's a science program to be able to make this radius measurement. And but you have to point your smartphone at the sun and let it take pictures of the sun, which is very, very bright. So the question immediately comes up, is it safe? Are you going to burn your smartphone to a crisp by trying to take a picture of the sun? And the answer is certainly not. You do that these smartphone cameras don't have mechanical shutters. They're always open. And so when you're looking at anywhere with the sun in the background, you're getting sunlight onto the camera. And so there's perfect safety in doing that. And so, but we had trouble convincing people, and there were people within NASA who were issuing warnings: "Don't point your phone at the sun because you'll burn it to a crisp." But but as many as, and we'd hoped to get, I kid you not, we'd hoped to get 1 million people lined up along the eclipse in 2024. We tried to do this in 2017, not very successfully. We made another minor effort in 2019 in South America, and those were failures pretty much on this side of the Megamovie cosmos. Megamovie worked fine, but the smartphone end of it didn't. And so in 2023, I was talked into start trying again by Gordon Emsley because he liked the idea. So we started from scratch and built an app. But let me tell you first about the beads themselves. Here's a wonderful picture, time sequence picture taken by Peter Horalik, whom I've never met, but who is obviously a Czech by his name. And here's a picture of Francis Bailey, whose name was given to these beads that you see just at the C2 contact and the C3 contact, ingress and egress of the sun from behind the moon. So C2 and C3. So not to go into too much detail, there are important scientific reasons to want to know what the shape of the sun is, and those have to do with relativity in a very complicated way. But you can see from the numbers here, the remarkable fact is that this. Okay, let me start from scratch. If the sun were oblate to a certain extent, it would affect the perihelion of Mercury. The orbit of Mercury would precess because there is a torque. If you put a torque on a rotating object, it will want to precess. And so, how much precession is there? You measure it in arc seconds per century. Okay, this is not much precession. So this orbit is going around the sun and it's rotating very slightly at that level, arc seconds per century. And already in the 19th century, and this is a real, says something really remarkable about how precise astronomy can be. Already in the 19th century, people had measured this precession of the perihelion of Mercury, and it came out to be more than you would think. So if the sun were oblate, more than you would think, and you can see the kind of uncertainty here. It's quite small. So anyway, so that's the scientific motivation, something like that. Let us see if it really is oblate, and if we understand the effect on the perihelion precession of Mercury. Okay, and this was the idea of Bob Dickey, a famous physicist, great guy, invented many things like the Dickey switch and that sort of thing. Okay, so I've already told you that SunSketcher is going to be based on smartphones plus app. It's an app and it uses the GPS. And the other input is the LOLA, Lunar Reconnaissance Orbiter database. This is measuring the surface topography of the moon, right? And the way it does it, and it's doing it right now, there's a lunar orbiter satellite that's actually has been there for I think going on 20 years and making continuous measurements of the solar surface via laser pulses. And you can see the pattern of it's an interferometric measurement that launches a beam down to the surface of the moon and gets its reflection, more or less like a radar, and in a pattern of 5 patches like this. So it's a differential measurement of local surface structure, and it's amazingly successful. It's so precise that the claim is that you know where every boulder is on the moon as long as it's as big as a few meters. And so we know the surface structure of the moon far more accurately than we know the surface structure of the Earth, partly because a lot of it is underwater, but also just because the measurement can be made in this way from space with no interference whatsoever from atmosphere and clouds and birds and things of that sort. So anyway, this database is building up, and we use it at the limb of the sun to actually um, map out the edge. Okay, I'm going to skip ahead here, like this. This is the way the eclipse looks, but from the point of view of the moon, there's this mountains and valleys, and here's the Bailey's bead that is occurring just in a specific valley at a certain azimuthal location around the periphery of the moon and the sun. And that timing is extremely precise because I think these lines may be drawn to scale with sort of a millisecond. All right, so the sun is moving very rapidly through this lunar valley, but that can be timed by GPS. Okay, so now back up. What actually happened was we got this very diverse group of undergraduate students. Gordon pulled them together at Western Kentucky University to build the app. And I can say that this is really was a nice experience because this group of students was in fact very diverse. So if you hear bad things about DEI, don't believe them because the students were all kinds of people. Name your diversity, your favorite diversity. In fact, the majority of them were female, but all kinds of female people. One of them was from the Bahamas, for example. So it was such a pleasure because they all came happily together and specialized in this and that and made this app. So and it worked, believe it or not. So we had a beta test of this in 2023 in Odessa, Texas. And we did the full up operation in 2024. We didn't get the million people that we wanted to, in spite of the fact that we had good support from NASA in terms of advertising. I think probably because people really were reluctant to give up their smartphone during such a fun thing as the eclipse, because you can take pictures of your friends and yourself, and it's a real ask to get somebody to just park their smartphone on a rock and leave it alone just during the most interesting part of the eclipse. But of course, that's the right thing to do. If you're a fan of eclipses, the right thing to do is to ignore your phone and just look at the eclipse. And I remember when Laura's actual words in 2017, she saw the eclipse, were, you can say it, Laura, go on, say it. Holy sh! I said, what?
Holy sh! Yeah, I
Yeah,
can't
that's right.
say
That's right.
it. Holy, yeah, I swore. I didn't even mean to swear. I was
Yeah.
being filmed.
So, so, so at that point, we'd been thinking about different things you could do with the smartphones, and another thing we could have done with the app was to actually record sounds. And so, maybe the next time there's a big eclipse, but it's not going to happen soon in the States. We'll do that. We'll record sounds, and you'll have this wave of "Holy shit!" going across it.
Well, the Soundscape folks did do that.
Was that right?
Yeah, so there's a NASA group that
Oh my
got.
goodness! My goodness. Okay. It's the wave of sound goes with the darkness, of course, of totality. So I'm
Right.
glad they did that. I'd like to.
But
I'll
they're
have
having
to.
the same, they have this, like we all are just have all this data now and we're trying to analyze it. So
Yeah,
they're having the
yeah,
same problem that we're all having.
yeah. I'm having this problem too, and I'll get to that. Okay, so in any case, we didn't get a million. We got about 40,000 though, which is pretty good. And I think with 40,000, if they had all been valid users, we could have maybe done some great science. As it is, we're still not there, but we'll get something out of this at some point. It's not so good because actually of these 40,000, this and that, but specifically the app didn't work quite right for Android. Worked fine for Apple, but we lost quite a bit of upload from the 40,000 people. So actually, the number of really good users was only about 2,000. So that's a pretty good database. And so it says here, data analysis underway. What that means is that I am working on this part-time and had been working on the data we got in 2024. Uh, and I have an assistant who's an undergraduate student at the University of St. Andrews here in Scotland, who's working over the summer with me on this. But it's a very small group of people analyzing these 2,000 times 100 pictures that we got. Okay, this is where the observers were. Uh, we were restricted legally to being able to get data only from within the United States. And so you can see that, in fact, most of the users are in the United States, and they stop in Mexico, although there are a few stray ones in Mexico, even out in the Pacific Ocean, and there are a couple or three in Canada in the water, particularly. And those are U.S. people who actually had their smartphones with them on a boat in the Pacific. When they came back, went home, and from a from their home internet access, they appeared to be within the continental U.S., and so they could upload images even from the deep, the deep Pacific. So there's a very nice eclipse track there, and there's a gouge out here where Lake Erie is, because there's a lake. Otherwise, it's a pretty good sampling, and you can see that in spite of the fact that the clouds do exist and there are patches where it really just wasn't good, there's actually pretty continuous coverage right through the whole eclipse track. It's quite good. Okay, so what happens when you try to look at these data? What are you trying to do? What you're doing is you're uh, exaggerated here on the left panel. You're looking at the edge of the moon, which is very lumpy. And there's a general astronomical law, which I think you probably all have heard about, namely the bigger an object is, the rounder it is, the smoother it is, simply because of gravity. And so the moon is smaller than the sun, so it's rougher than the sun. The sun is actually quite smooth, and the moon being smaller is quite rough, rougher than the Earth, for example, because the Earth is larger. And so these are lunar mountains, and in this left-hand panel, they're still small. I mean, the mountains on the moon are not totally gross deformations of the body of the moon, but they have to be amplified here by a factor of 1,000 to be visible, right? So, but they're real. And if you look at them not on a circular projection like this, but a linear projection, uh, it's a function of azimuth, right? The radius. If you go around the moon, this is the rough structure that you're seeing here in the orange line, laid out in 360 degrees as you go around the moon. And the way the sun looks on this projection is like a parabola that comes up, and it comes up and kisses the moon just at a point, and that point is a Baily's bead, or it kisses it at a different point if you're at a different observer location, for example. And so then, because of these sharp structures and this parabola, you're able to actually localize your measurement quite well around the azimuth of the moon. So in principle, we have information about the shape, not just the oblateness of the sun by its lunar reference, but also the higher order shape components if they were to exist. In an ideal measurement like this, we would be able to look at the time variation as well, because it takes, as you know, an hour for this to develop. And so if the shape of the sun were changing during that hour, then we would, in principle, be able to monitor it. Next time, this time, and this is what I was saying about different observers being able to look at different places. This is the 360 degrees, and these little parabolas are for different people at different distances from across the track, right? From one side of the track to the other, you get this whole range of azimuths, and it turns out. And in this case, there are 20 or 30 different actual valleys, the different physically different beads that we could have seen we did see. Okay, so this is a movie of one smartphone. So you can see it, it'll play slowly a couple of times. That was for second contact. That flash there was right in the middle between contacts. And here comes third contact, and there it is, very bright. And so we set it up so that we got high cadence at the contact times, half second spacing between images, all still images, all JPEGs, and we got one image right at the center in order to localize, to do photometric reference and to localize. And so you can see also that these images are not very good, but that's the best you can do with the smartphone. And the actual center eclipse, the full eclipse corona is flashed up there, isn't, it has maybe 30 or 40 pixels that are physically independent. So it's a very, very poor image, but the timing is precise. Okay, so uh, here's the whole array of 101 probably images, or maybe this is a fraction of them. And here's this one in the center, which has the actual corona. And here's the ones up here that show C2. And here's the ones down here, which show C3. And this was from user number one, ID number 977. And we learned from his GPS or her GPS data that this was at 1.488 seconds, right? So we have the time tagged to a millisecond, and we have double precision latitude and longitude and height. This is 0.379199998 kilometers. So we really got excellent data from these users. Okay, and there are a couple more users. There's good old number 1024 and 1033. And in each case, I'm showing you the central image. You can look at it now and see how bad it is, and the second and third contacts in both cases. And you can see that the second and third contacts are at very different locations, right? Especially here and here, because these users were pretty far apart in the cross-track sense. And so we can exploit that, and that's what we're working on. But the analysis is not easy. Uh, the hope was if we'd had 1 million users, we could have gotten very great precision just because of the square root of n, right? The statistics just get better and better the more data you have, as long as you understand what your systematic errors are. And so with 1 million, we would have had a good chance to winnow out systematic errors and make a good measurement. But with only 2,000, it's unlikely that we'll get to a competitive kind of measurement that way. But we're still working on it, and that's still 2,000 is a lot. All right. So, and this is what the timing looks like. If you do the photometric reduction of one user, I forget what user this is, but you can see that the second contact here is right at that point where my arrow is. You can see my cursor, right? Wiggle,
Yep.
wiggle.
Yeah, we can see
Okay.
your cursor. Yeah.
Uh, okay, and here's the central image right in the middle, and here's the third contact, and there's what looks like a very sudden increase, a very sudden decrease, a very sudden increase. So how do you time that? If you blow up the actual points in the second contact, you see that it's got kind of a straight part and a flat part. And so the intersection of the straight flat parts would let you actually, produce a reference marker. And that would be, but you can see also that it's happening over a period of many seconds, right? So this is not the milliseconds. This is seconds. If it were milliseconds, it would be better, but it's seconds. And so it's a case of interpolation. We'll have to make a serious interpolation, and we may or may not get it right. But whatever we do, it's an arbitrary definition of where this inflection point is. So this is, in a sense, the way you would measure the size of the sun from this time, actual time. But since it's such a crude measure of the radius, it is actually only good as a differential measurement as you go around the sun. maintaining the same definition and applying it to all the data gives you a relative measurement about from north, south, east, west around the limb as opposed to an absolute measurement. So what I've got the student in St. Andrews working on this summer is to actually measure the radius. So she will come up with a number for the actual radius, but only based upon some arbitrary definition of what is the actual physics of the limb of the moon. And I'd like to ask you guys a question about this. Let me just go down to go back up to this Czech photographer's wonderful image. You can see around, uh, not just at the bead location, which is, let's say, this point, but all around the limb, near it, there is brightness. And here's another excellent example. Here's a singular, unique, beautiful Bailey's bead point, but there's brightness all the way around the limb. And so the smartphone picks up all of that stuff. And because its resolution is not so good, it makes it lumps it all into a one brightness. So the question for you, Laura, I will let you speak for everybody, is what is that? What is causing that extended brightness left and right around the Bailey's bead? Or Darlene, you look interested. You can answer. I mean, I wouldn't ask this question if I knew. So I don't know what it causes it, and I haven't seen this discussed very much. Maybe it's in the literature somewhere,
And you're not
but
talking about just the chromosphere, though clearly the red pieces are I mean, it's the chromosphere, right? But
that's
there,
right. That's right. But why is the chromosphere so bright, 10, 15, 20 degrees away from the bead?
mhm.
So this is uh, I have
Is
a
that just a
conjecture.
timing issue?
No, these are snapshots.
Right, but if it's a millisecond phenomena, presumably they didn't have millisecond timing, exposure time.
Well, yeah, that's right. Well, certainly it's a finite amount of time for the exposure. By the way, we had to operate at the maximum speed of a smartphone camera, which is 1/80,000th of a second. That was turned out to be the correct exposure time for the beads in the data that you just saw there. Yeah, but so this is like a 10 microsecond exposure, let's say, and it has this brightness all the way around. And
Hmm.
so I have a conjecture that I have not dared to mention to uh, Ernie Wright, who's my NASA friend who knows about the Lola database. But
It's not I mean, it's not refraction. The atmosphere is not.
that's correct. It is. It can't be refraction. It's got to be
Yeah.
something on the moon or on the sun, but not the sun because the sun is very smooth. So it's
Mhm.
a
So it's like some
lunar.
reflection, maybe.
The
Yeah.
question
So
in the chat is, couldn't it be
my
inner
conjecture
corona?
is just that. Oh, there's a comment.
Yeah, couldn't I put this in the chat, but couldn't it just be inner corona?
That's a chromosphere.
No, I don't think so. The corona is just not that bright. Uh, but
Yeah.
but that's an idea. So that kind of thing. I haven't actually tried to be
Because
quantitative.
look at like 12 o'clock on this image, and you can see these like peaks of, right? You see that coming up? I mean, that's corona,
Absolutely.
right?
Yeah.
So I guess the question would be, what was the exposure time? And is it such that you could exclude corona? I'm not sure.
I think the exposure time is a red herring. But I mean certainly there is corona. I mean, so the corona is down there, and so if the corona had an oblateness, a systematic scale with a dipole pattern, maybe
Yeah.
that could do it.
Well,
Maybe
the
that could
corona
do
is
it.
not symmetric, right? So,
That's right. That's right.
um, interesting.
Yeah. So
That is a good
uh,
question, though. It is odd.
yeah, I think
Well,
it's a
yeah, and I mean, if we could call it the chromosphere, just because the chromosphere is so much closer than the corona, that like it really is this. I guess what's confusing to me, if it were just red, right, then it would be. then I think we're looking at a different way. It comes back to the wavelength question, I think, at the very
Yeah.
beginning.
Yeah.
You
But
almost
don't
need a
forget
spectrograph.
the chromosphere is very, very thin, right? It's an arc second. If you project it, it's a couple of arc seconds in thickness, right? So it's a couple of arc seconds, might explain what's near the bead, but not what's far from the bead.
Hmm.
Are you able to get any measurement out of it? Is it symmetrical around the beads?
What
Is
you're what,
is
what
it
you're seeing
longer
is
on one side than the other?
it may be that your images. I mean, there may be images in the Megamovie data sets that are good for this purpose.
Yeah.
The case, what I'm saying is that we can't really tell much from our data, and the what causes this lengthy, unfortunately long, smooth variation here is just a lot of that excess brightness around the limb of the moon, not the Bailey's bead itself, but just that brightness, I think. So I haven't tried to think hard about this in the sense of actually trying to put numbers to ideas like yours about the corona, or like Laura's about the about the lunar scattering, until we got a bit further along here. But every now and then I meet people like yourselves who are experts in eclipses, and I ask this question, and pretty uniformly the answer is, "Gee, that's interesting. I don't know really." So I don't know if we really do know. So anyway, stay tuned to that as a possible limitation of what we can do with the sun sketcher here.
Yeah, and
Uh,
Hugh, definitely send us the times that your students are studying because we can look in our data set and see if we have some diamond rings during those times.
well, actually, thank you for suggesting that, because the so I'm thinking about Spain in next year, and Egypt in 2020, is it 2027 maybe,
I think
to do
7.
to get more data. And the question really comes up, do we want to stick with smartphones, which are really nice and neat and give many people a chance to participate? Or do we, if we really wanted to make the science measurement right, shouldn't we do something like Megamovie instead and just get nice crisp images of this feature? And
Well, there are
so
lots of people that want to do more Megamovie, so we have a base.
well, it has to be a Spanish base.
No,
So
no,
if
I
we're
know. No, we have people who will travel to Spain
okay,
and
well, that's
other
good.
places. So
Oh,
we
that's
just,
good.
yeah, so we can, we'll basically be doing it. Let's just say we're going to do it, Hugh.
So the Spanish eclipse is going to be not quite so good as the Egyptian eclipse, which
Right.
is unfortunate. That eclipse, it does go through all the war zones. So
Well,
Egypt
maybe
is
they'll be done by then.
maybe. Anyway, so let me just give you a bit of an anecdote about this. This is our we did test observations with the app in 2023 during the partial, and so here's a picture of the Western Kentucky team wearing Western Kentucky red t-shirts, as I am doing myself right this very minute. And here are these long eclipse shadows, and you can see an eclipse kind of sky. West Texas sky is always extremely clear. And what is this? It is Stonehenge. Okay, in Odessa, Texas, there is a 70% scale model of Stonehenge accurately. So some
This is
person,
Spinal Tap.
yeah, some rich Texan who owned a rock quarry had some extra rock, and so he gave it to the University of uh, Texas Permian Basin, which is based in Midland, Odessa, and they built this Stonehenge. Okay, and here's your Spanish eclipse coming up. Uh, I would actually like to be in Iceland. That would be good, but it's like much likelier to be cloudy, so I'm probably going to position myself here in the Basque Country in Santander or someplace like that. Uh, Although there it goes over Ibiza, right? So, and here I've written in many languages what's going to happen here. Okay, and there's the one in 2027. Ah, yes. Okay, and here's the prime spot: Egypt, the high desert, uh, guaranteed to be clear, and this is, I think, where we should go rather than Libya or Yemen, for goodness sake, but Egypt. Okay, that's all I have on slides. Thank you very much. Am I finished already? Is it? Yes, I think I'm finished. So thank you for listening. If there are questions, please ask questions because I would like to explain more about our analysis if you wish to know about that or whatever I can do.
There was a question about could that light be some gravitational lensing? Does the moon have enough mass?
Yeah, that's another good idea, and the answer I think is no. But yeah, keep those ideas coming because I do think it is at least in people of our sort of expertise, it's not well explained. And by the way, just a sad note that Fred Espenak has passed away.
Yeah.
Uh, Quite unfortunate, a great guy. And if I had asked him this question, he probably would have straightened me out right away.
Yeah.
So too late.
Yeah.
So Hugh, I asked in the chat, so if we wanted to do something other than smartphones, to get the kind of timing you're looking for with the telephoto lens, maybe the thing to do would be to use video cameras, maybe, because you can do 4K video, pretty high frame rates now.
Yeah, any SLR with GPS,
Yeah, but
you
still
can do.
images themselves might not do it.
Well, still,
But but
we agonized about that for the smartphones. We could have taken movies with smartphones too. And the I was worried at the millisecond level about the our ability to understand the timestamps.
mm,
Uh, so with the stills, it was a simpler matter. Uh, but we only got a very few images, right? So if you take a movie, you get at the movie rate. It's all each one is an independent observation. So I think really that would be the right thing to do, and it would be. So this is the dilemma, the question about smartphones or real cameras.
mm.
So the doing it with real telescopes or real cameras gives you infinitely better resolution, spatial resolution, and you can do things like and also sensitivity, right? So you can do the movie imaging on at very high rate if you set it up right.
Yeah, as
So
someone's pointing out, there are other technical issues like when you start to get the beads and then emergence of the sun, you start to risk, damaging sensors and stuff. So it's a very dicey proposition. But I'd be curious, like I have a GPS sensor, like could you integrate a GPS sensor to provide the timestamp on your video? I mean, there are software for that, I think.
yeah, I think that could be done. But you're
I can
right.
Oh, Chris?
I can answer that. It depends entirely on the camera, and it depends on well, basically it's firmware. So I in 24 recorded using Blackmagic cameras,
Hmm.
and I was able to get stuff, but there are issues. Okay, so it all depends on the cameras. It all depends if they're like a 3 CCD camera or if they're a single sensor. It depends on the size of the pixels. It depends how well you can focus it because I had issues focusing. Um, One of the cool things about a lot of video cameras now, especially like the Blackmagics, is I can enable something called focus peaking. So um, like mine are actually pretty cool. They're professional grade cameras. They're studio cameras, and I hook up a follow focus, which is this little knob on the side that lets me change the focus. On the screen in the back, um, if I have my focus peaking turned on, I've got red outlines on
Hmm.
everything that's in focus, but it's not that precise. So I actually had it zoomed in using a 6K cinema camera at f7 on 11-inch Schmidt Cassegrain, and it looked like it was in focus. But when I'm actually doing it, it's not that
Ah.
focused as I like. So
So
let me.
Chris, what about burning out your camera? What was your experience with that?
I covered it up once I saw Bailey's beads. As soon as I had that bright flash, I covered it up. And in fact,
Yeah,
let me see if I
yeah.
can get my video because I have it on YouTube.
Hmm.
Go to YouTube. Where are my videos? My
I will
videos.
try to stop sharing if I can figure out
Oh, here
the
we go. So This
I
is
already stopped your sharing, Hugh.
no. I'm gonna put
Okay.
this. I'm gonna put the YouTube link in chat so anyone
Oh,
can
but
look
you
at.
can share if you want, Chris.
No, not really, because it's a YouTube video, so it ain't gonna look that good. I mean, I can, I guess, but I put the link there. And hang on. All right, fine. Share
It's
window.
better for our video recording, for
Oh,
sure.
okay. Well, that's a good point. Screen two. Let me get application. Screens, which one? Because I've got so many windows open.
It is amazing, though. Holy moly.
Here we go. Let's just do this one. Yeah, there we go. Okay, and share. All right, so this is nice and big. Uh, Everyone can see it?
Yep.
Yeah,
Cool.
see it. Help,
Okay,
help.
I'll just kill. So this was as sharp as I could get it, and this is with post-processing as well. So you can see it's not that terribly sharp. And um, I thought I could get it better. And this is with a 6K cinema camera.
Hmm.
So that's that's as good as I could get it. And then I had to move it over, and I had a weird cut. I had sensor or not sensor issues. I had recording issues. I was using
But
Jumper.
Hugh, that would be orders of magnitude higher resolution than you were getting, right?
Absolutely.
Spatial resolution.
Absolutely. Even if you didn't get the focus right, it would be infinitely better than
Okay,
a
well, let's
smartphone.
do this. I'm gonna jump over here right till we get. Yeah, there we
I
go.
know. I was noticing that the area you're going to, you can see the growing of this
Oh yeah,
line that Hugh's asking about.
yeah. That's
Yeah.
why I shifted the focus over to here.
Yeah.
And even at f7, this is like long focal length. So yeah, you can see that little Y that was forming
You
there.
see, you can certainly see the corona there, but you could also see this bright thing, which is not the
So
corona.
that's all I got.
Yeah, I
And
almost think it
then
is scattering off the moon.
yeah,
It
and at this
Yeah.
point, I was like, oh crap, I gotta put something on it. And so I put the filter on it right about now-ish.
Yeah.
Good.
And then you
Safe.
can see the very edge right there.
So just you just have to be
Oh,
ready to
there it
put your
is. I didn't see it
yeah.
there for a minute, but
Yep. So
Oh
and
yeah.
that was it. So yeah.
can you? Oh, well, we can back out in ourselves, I guess.
So it's red. It's
Yeah.
chromospheric brightness.
Well, yeah. And this was with the I had a full aperture glass filter on the front. So
Okay,
I
but
was actually running around putting filters back on all the cameras, all the scopes.
it's not a red filter, right? It's neutral density.
No, it's a white light filter.
Yeah. Yeah.
It's just that the color space of the camera
Yeah, it's the
made
camera.
it red.
Okay.
So
Okay.
yeah,
Yeah, that's another great complexity. I mean, the color response of the camera is a limiting factor, I would guess, if
it
we had
is
gone
because
somewhere.
it's that I think it's like this one I think is a 10-bit. Yeah, this is 10-bit color. So it's not terribly great. I
Yeah.
had lots of technical issues. Fortunately, because I did a live stream for this, and I drove 1,000 miles from Dallas Fort Worth to Indianapolis because it was supposed to be cloudy here. And 10 minutes before, the rest of my family went down to my cousin's land, which was like 20 miles off of the center line. So they got like an extra almost minute or 40 seconds from where we are here in Fort Worth. And they said that, oh yeah, it cleared up like 10, 15 minutes before totality, clear throughout totality, and then clouded up about 15, 20 minutes after. And we had high haze in Indianapolis. We could still see it really easily, but it was just a high haze. So,
We had, by the way, we had a cluster of users in Indianapolis in the Speedway. They
uh,
were actually
we were up
uh,
in, where was it? Carmel? Yeah, my uh, wife's aunt's husband's sister and her husband. It's confusing. We're all Polish. It's the Polonia. And what's funny is I actually know them better than my wife does because they were all friends of my parents when I was growing up, while my wife was in Poland and she had like met them just once or something.
So, can you pronounce your name?
Wodnicki.
Modnitsky.
Oh,
Okay,
I'm
Modnitsky.
Polish. Ja się urodziłem w
Kłamcie.
Polsce, to ja po
Okay,
polsku
okay.
mówię, dla mnie nie ma kłopotu.
Okay, excellent.
So I was born in Poland, so I speak Polish. We grew up speaking Polish in the house, and I came here when I was 3.5.
So many
And
people who are not Polish can't really speak, translate Polish names. That's all I'm saying.
uh,
But Modnitsky, I can do that for you.
I have a 9-year-old boy. I hope he's upstairs taking a bath right now, and his first language is Polish because everyone in the house just spoke Polish when he was, little. And then he started learning English. So bilingualism is good.
I think so.
Agreed. It's good for our brains.
It is.
All right, so that's my input on the cameras. So it's that brightening effect. I mean, you could see it just blew everything out. So I'm not sure how effective that
But
would
you can
be.
kind of you can see because while you're talking, I've been looking at that little spot right when it brightens, and you can see a mini diamond ring before it explodes.
Yep.
And so there's some interesting timing there. So Hugh, that might be one of the ones you're studying with your data with the Sun Sketcher data. So it'd be
Well,
interesting.
in Indianapolis, for example, would be
Yeah, so you should take that. It also makes me think back to the wavelength question. I think you've got to, it's almost like what like you should just pick like a green line and just have a green filter, like just have like a notch filter on your cameras. Uh,
yeah. I
that's
think
like green.
if we did this sun sketcher business again, I think what we would do is give people a color filter
Yeah.
to first
Yeah.
of all to reduce the exposure, uh, and yes, and that would be it would make the precision of the final result more independent of the color the erratic colors different cameras give you.
Oh,
That's
So
right.
wait. I have one suggestion. Because I was trying to do this and it didn't really work out. It went fine on the live stream, but it needs more data processing. What if you use a hydrogen alpha scope?
Yeah, I was speculating on that on the chat, Chris, and I
Okay.
think probably you're too narrow then, right?
Well, not
There's
necessarily. Here's what I
no
found
for
out.
beads though.
But
Well,
not for beads because then you're going to see prominences and you're trying not to see
yeah,
prominences.
yeah, I think
Yeah,
to
but
avoid
that's the
H
thing. I think
alpha.
just I'm just thinking that that's
You
sort
got
of
to clip
the
out H
extreme.
alpha.
That's
Yeah.
the extreme of your notch, Laura, right? But there might be some sweet spot, right, where it's
Well,
narrow
I think
enough
you would do
but not too narrow.
green. You'd want to do green if you're trying to find the max, you want peaks in the green as the visible.
Actually, if
Right.
you go into the far into the red as possible, you get better seeing.
okay.
So that's another factor.
The hydrogen alpha may not work, and I'll show you why not in just a moment too, because there's this limb darkening with hydrogen alpha,
Mm,
and it's
yeah. You
it's
just
bad
lose so
enough
much
that
intensity.
yeah, it's trying to get that focus right on the edge is really, really hard. And I have a video of this somewhere here. Yeah, there we go. This is the quick one. That's the quick one. Uh, oh, jeez. I hate commercials. I really do hate commercials on YouTube. So skip that thing. And I guess
But
I'll
you're
share
not
this
sharing
one.
it, right?
No, I put it in the chat and I will share in just a moment. So this is one I did with eh, 3.5 hours of data, something like that. So when you look at it, there are the spiracles
Oh,
on the
that's quite nice.
edge.
Very nice.
Yeah, yeah. So like I'll keep it
Oh
going.
boy, that's great.
There, there are the spiracles here that are going off, and so that's what we'd be picking up. But
Spicules,
yeah,
spicules.
spicule, sorry. And it's this little region right here. That's going to be the first region that pops up, and it's so dim. And
Yeah,
I didn't get this without a lot of processing. So the way this one was made, I
this
took.
is it's exquisite. This is really
Oh,
a
thank you.
wonderful. Yeah,
So this is kind of neat, just showing the scale here in a moment.
yeah.
The way
Stunning.
I did this one is I actually took a minute of exposures. I think it was three to five exposures per second on an AS, no, this was a QHY. Yeah, I think this is a QHY 183. So it's 183 chipset in mono, which is with the 80 millimeter lunt. Um, and I've got single stack and double stack, but this was single stacked. It's just enough that the sun fills almost the entire field of view. So that's pretty good. But I took 1 minute worth of exposures, and then uh, processed those with oh shoot, what's that? Uh, uh, oh, it's some software. I can't remember what it is off the top of my head. Um, Auto Stackered. That's it. It's Auto Stackered. I took those images for that 1 minute and then took the best 10% of them and stacked those and processed them, then processed them again in Photoshop and then built out the frames and then put everything together. So just looking at the raws, you really couldn't see the edge very well. But
Well, and your
that's
time resolution is shot too, then, if you have to do all that stacking and binning.
exactly.
Well, but not so bad that you can't see things happening in the active region there. This is
Yeah,
really quite good.
if you're doing it,
Look at that. Look at those flashes.
yeah, every frame is 1 minute. So yeah, you can see the activity, but it's that edge stuff. And actually, you can actually see it rotating. You can see the rotation of the sun over that 3.5 hour time too.
Absolutely, absolutely. So
Just a
this would
little
be,
bit,
there's
but
this
yeah.
other question about the Wilson depression, right? So if you had a big sunspot going around the limb, you would have enough. These images are good enough to be able to distinguish between whether it's really a dimple or whether it's just an
Oh,
artifact.
oh, that's cool. I didn't think about that. So this is
Yeah.
the northern polar region. I did this thing using the Solar Quest mount from what is it? Green Company, Skywatcher. And so I had to then derotate everything within Photoshop. So that was a massive pain. But it was all doable. Um, yeah, that's my only issue is that I could get if I single stack it, I can, and I have a big enough pipe going to the hard drive, or in this case, the SSD. If it's fast enough, I can do full frame recording at up to 8 frames a second for the RAWs. And then you can process those. It's easier if you do an SCR file because yeah, that's the setup I was using. Um, 3.5 millisecond exposures. Oh, I had 11.5. Okay, well that's cool. So this is 11 and a half frames a second. That's not too
We,
bad then.
you were showing us 1 minute sampling, all right?
Yep, 1 minute captures. Oh, best 1%. Okay. And auto stacker in Photoshop. So
You can
yeah,
really see in your images too why it's brighter with more sunspots. Because if you go back to the just a couple, you
the,
can
the
see
full
how there's
frame.
all the brightness around each
Oh
of
yeah.
the sunspots.
Yeah,
So
yeah.
that's what he was discussing earlier, that
This is what we call plage. This is H alpha, right? So you're seeing the
Yes.
chromosphere, but it's closely related to the faculae. But you see the plage is not so restricted to the limb. You can see it at the center as well.
Yeah. And then there's a little bit
I'm just gonna see
here
that
too.
last episode that you seen by
So
myself.
okay, that's all I got to show. I'll I'll shut up now.
it was awesome.
Thank you. This
Beautiful.
turned out
Yeah,
to
it's
be
really cool
a
stuff,
fun
Chris.
show.
Really great, really great.
Yeah. I actually have last May, yeah, last May I have I tried to do it for like 9 hours. And so I've got a ton of data on my big old NAS, like I think a terabyte and a half of data, and I just haven't had time to process it.
Yeah, that's a lot of data. That's what we have from you all.
Yeah, it's
We're
like
still
it's something like
processing.
9.5 or more. It was in
So,
May, so it's
so
it's like I tried to
Chris,
do sun up to sundown, and it's just too much.
I've
Yeah.
got an anecdote about terabytes. So as I told you, I'm quite old, and so I visited Boulder in the late 1960s and visited NOAA, and they had the terabyte memory. There was only 1 terabyte memory in the whole world, and they had it, and it was a room about the size of your living room, maybe bigger, and it was staffed by people wearing neckties and running around. It was amazing, but it was a terabyte, and now you can get a terabyte on a jump drive. Uh,
It is
there it
insane.
is.
It is. I know. Times have changed.
It's amazing. So
Well, I think
Laura,
we're at the end, and we should
Laura,
let
Laura.
Spencer.
I put the background up for you.
Oh yeah, holy Eclipse Batman is back.
And,
Yeah,
and I am probably as old as Hugh.
Maybe,
I,
maybe.
I would make a good guess that I'm your age.
Yeah, we're doddering, aren't we? We're both kind of in that.
1951.
You were born in 51? I'm 12 years older.
I keep telling you, Hugh, no one's going to believe you when you tell us.
Well, I can tell it when I'm going. I'm living in an upstairs flat here in Glasgow, and it's the stairs are killing me. I can tell you that. So,
Or
but
they're keeping you alive and just hurting.
oh yes, maybe that. Okay, well, thank you all. This has been very good for me to talk to real astronomers again. Since I'm by myself doing this data analysis, I need encouragement, and I'm lucky to have the student in St. Andrews, and so I'm hoping to make progress. And by golly, we're going to write a paper if we get anywhere.
We
So
are
thank you.
here to cheer you on,
Good
Hugh.
luck.
You got
Good luck
this.
with. Okay, good. Thank you. Thank you.
Thank you. That was awesome. So fun.
Okay. See you
All
later.
right.
Good
This
night.
ends our evening. We'll see you all in a
Bye.
month.
Yeah, thank you, Hugh. Thank you, Laura.
All
Bye,
right.
everyone. We'll send out the
Thank-
recording.
Yeah, bye,
Thanks,
everyone.
everyone. Turn off the recording.